The next thing we're going to take a look is making sure that we are using correlation and regression wisely. Remember that correlation and regression are powerful tools for describing the relationship between two variables. When you use these tools, you need to be aware of their limitations. Number one, the distinction between the explanatory and response variable is important in regression. Remember that switching the x and y variable definitely changes the least squares regression line because your two variables are switched, your x and y values are switched. It's actually going to be the inverse and it's going to change what the equation actually looks like. However, remember that switching the x and the y does not change the r value. So when we switch those, the correlation or how tightly they fit about a line does not change. Okay, so just take a look at this. Number one, we're taking a look at the miles driven and then the cost and price of dollars of a car. Here's my least squares regression line. Here's my standard deviation of the residuals. Here's my r squared value. Now notice what happens when I switch the x and the y values here. I have the miles driven on my y-axis and the price in dollars on my x-axis. Now, if you notice, the y-intercept changes, the slope changes, the standard deviation of the residuals change, and look at your r squared. Notice it is exactly the same. It did not change at all. So that is telling us still that the same amount of variation in the response variable can be explained by the least squares regression line that relates the two. So just be aware of that. Correlation and regression only describe linear relationships, so please be careful with that. You can calculate the R value for any relationship that you have. However, it is only useful if we're dealing with a linear relationship. The first thing that you're always going to want to do is plot the data. So this one is a linear relationship, we're good? Not. This one's pretty good. This one is linear. It's just a vertical line. So you have to plot the data. And if it's not linear, we're just not going to go any further. Okay. And notice how this R value is pretty strong. So R says 0.816. Okay. However, this is definitely not a linear equation. So we cannot use the R value to make predictions. Now, correlation and least squares regression line are not resistant to outliers or points that are unusual. One unusual point in a scatter plot can greatly change the value of R or the correlation. The least squares regression line is not resistant to points that are far off of the regression line. Take a look at our graph that we have here below. We're comparing the age at which a child said their first word and their Gazelle score. And their Gazelle score is just like an academic score. So take a look at child 19 and child 18. Both are far off the regression equation. Child 19 has a very large residual. Okay, it is much higher than the rest of the points, where child 18 does not actually have a very high residual, but it is really far away in the x direction for the rest of your data. So this is actually far away in the x direction, and child 19 is far away in the y direction. Let's see what those 2 points do to the equation. Now, let's see what happens to r squared in our equation if we remove child 18. So here's child 18 right here, okay? So this, if we remove it, okay, the r squared value is going to be 11%, okay? Now, take a look at what the data is with all of it. Actually, r squared is higher with child 18 in it. Okay, so now let's take a look here. With all 19 children, our R value was negative 0.4 and our R squared was 0.41. Here's our least squares regression line. When we remove child 18, take a look at what happens to your R value and your R squared value. It actually goes down, okay? Child 18 is an outlier since it's far away from the other data points, but it has a really small residual. However, when we remove child 18, okay, the line actually changes quite a bit. This means that child 18 is an influential point because it influences or changes the slope of the line. So take a look. With all 19, the slope of the line was negative 1.127. With child 18 removed, it was negative 0.779. It became a lot less steep. Therefore, in this case, it's an outlier. Okay, the reason it's an outlier is because it's far away from the rest of the data. It's an influential point because it actually changes the slope. Okay, if something changes the slope and changes the R squared and the R value, then it's influential. You cannot guess on an influential point. You actually have to compare the slopes and the R squared values to see if they're the same or different. Okay, now remember that we're deleting data points only to investigate their influence on the least squares regression line. In practice, you would never delete an outlier without justification. Now, let's take a look at what an outlier and an influential point exactly are. Keep in mind that there are no rules for determining outliers or influential points in scatter plots. You'll need to be able to explain what effect any point has on the correlation, the slope, the y-intercept, the standard deviation, the residuals, and R squared. The least squared regression line makes up the sum of the squares of the vertical distances to the points on the line as small as possible. A point that's extreme in the x direction with no other points near it pulls the line towards itself, just like that child 18 did. We call that influential. They change what the least squares regression line looks like, okay? So like I said, it's an influential point whenever it's far away in the x direction. So you have your points up here, okay? And then you have this point all the way down here. It's really far away from the rest, but it has a small residual. So that's most likely going to be your influential point. An outlier is an observation that's outside the overall pattern of the data. Points that are outliers in the y direction, so they're high residuals, but not the x direction, are going to have large residuals. The outliers may or may not be influential. So you're picking first. First, you're deciding, okay, is it an outlier? Okay, you're going to say, yes, I have an outlier. Then you decide, is it influential? Yes. Or is it influential? No. So influential yes means it changes the slope in the y-intercept. Influential no means it's not changing anything. An observation is influential if removing it changes the result of the calculation, changes your least squares regression line. Points that are outliers in the x direction are often your influential points, but you can't guess. You have to actually remove the data and see what happens. Then here's your general rule of thumb. Your general rule of thumb is outliers is something with a large residual. Influential points is when you remove them, it actually changes the regression line, okay, which means it changes the slope, it changes your R and your R squared. Usually they're extreme in the x direction, okay, and then they often have a small residual. So they're not too far from the line, they're just far away from the rest of the data. Now, let's take a look at this example below. Does the age at which a child begins to talk predict a later score on a test of mental ability? A study of the development of young children recorded the age and months at which each of the 21 children spoke their first word in their Gazelle adaptive score, which is the result of an aptitude test taken much later. The data appear in the table below along with a scatter plot, residual plot, and computer output. Should we use a linear model to predict the Gazelle score from his or her age at their first word? If so, how accurate will your predictions be? So take a minute, try this. What you're going to do is put the data in your calculator and answer the questions on the next slide. So this is the child, and then age is going to be all of your X's, and your score is all of your Y's. What I would like you to do is make a scatter plot, describe the scatter plot. We've talked about that. Make a residual plot and then tell me, is a linear model appropriate? Find the least squares regression line and graph it. Write the least squares regression line in context. Interpret the slope and the y-intercept in context. By hand, okay, interpret the R and the R squared value in context. And then tell me the standard deviation of the residuals is 11.0229. Please interpret that. Are there any outliers or influential points, and how do you know? Go ahead, take a minute, try this, and when you're ready to see the solution, go ahead and hit play. All right, so let's take a look. This scatter plot here, if you're looking at part A, shows a moderately strong linear association between age at first word and the Gazelle score. So there are a couple of outliers in the scatter plot, child 19 and child 18. So child 19 has a very high Gazelle score for their first word, and child 18 didn't speak his or her first word until much later with a lower Gazelle score. The residual plot does not have any obvious patterns, confirming what we saw in our scatter plot. It looks linear, so a linear model is appropriate. Now, let's find the least squares regression line and graph it. You're going to get that from your graphing calculator. Here's your least squares regression line. The predicted score on the Gazelle is equal to 109.874 minus 1.127 times the age of their first word. So here's your slope, okay? Interpret the slope in context. As age at first word increases by a month, so if you want to put it like this, I always do this over 1, and I know that X is on the bottom, so this is age of first word, and this is Gazelle score. It just helps me to interpret it. So I say as the age, and this is a plus sign, of the first word increases by a month, the predicted Gazelle score is going to decrease by 1.13 since you have that negative sign. What's the Y-intercept? Okay, the Y-intercept, remember, is always going to be 0, Y. So if a child spoke their first word at 0 months, he or she would have a predicted, and notice how the word predicted is important here because we're using our line to predict, Gazelle score of 109.87. Let's take a look at our R value and interpret the R squared in context. So our R squared is going to be 41.41% or 0.41. So that's telling us that 41% of the variation in scores can be explained by the least squares regression line. Now make sure you state that relates ages and Gazelle score. Okay, here's your standard deviation of residuals. Remember, that's telling you how far away on average the observed is from the predicted. So this means that our predictions will typically be off by 1.0229 points. Now, and remember, since your residual is in the Y direction, we have to use the Y information for our interpretation. Were there any outliers or influential points? So we already discussed this. So child 18 and 19 are both outliers. Child 18 is far away with a high residual, child 18 was far away in the X direction. Child 19 has a high residual. So child 18, as we discovered, is both influential and an outlier because when we took it away, it actually changed the value of the slope and the R. All right, so just one final tip is that association does not imply causation. So as association between explanatory variable X and response variable Y, even if it's strong, it does not mean that there's good evidence that the values in X actually cause a change in the values in Y. Okay, so here's an example down here. Go ahead, take a minute and read it. Okay, it's just kind of an interesting example. But it does not necessarily mean that correlation implies causation. All right, and this is the section summary. Go ahead and take a minute and read these over. If you have any questions, please let me know.